Hello YouTube, De-bodgery here, aka Richard Gumpha on Facebook. Welcome to EV Components Review. On the bench is the macro video for the BBS HD controller. This is the locked version. I don't know much about these controllers. This is something that's simply not something that I would use for anything that I would do. Other people that are really familiar with this, feel free to correct me where I make mistakes because, well, I'm probably going to make a few. Anyway, I'm going to make another video after this one that is going to talk about how I think you can possibly unlock this. But this one here, I just want to go through the components on the board. So anyway, expect that one in a minute. Folks, if you like my video content, please subscribe to my channel, leave comments, thumbs up, hit the notification bell, all that kind of stuff. Alright, so let's move on to this thing. This is the daughter board, or the I/O board, or cable board, or whatever you want to call it, where all your signals come in and out. This is a headlight connector, meter, speed, battery, Hall, PAS cables. So that's basically everything that's here. I don't know what speed and meter do per se, so all you Bafang people, you can tell me what that is. The other ones are pretty obvious. The red wire here, so that's 5 volts. This red wire is also in parallel with it, that's 5 volts. And that brown wire right back there, that goes the battery cable, and that's also 5 volts. I know that because those ones all are connected together, and probably that red wire is too, and probably this one in speed is also 5 volts. But I don't really know about those ones. Maybe this red wire that one's probably 12 volts. But anyway, yeah, probably all these other smaller ones where there's a red wire, that's probably all 5 volts, with the exception of that brown one over the battery cable. That one is 5 volts as well. Green and orange, those are CAN bus from the battery pack, and that's that big connector right here. So yeah, you can see in there those three same wires. So orange and green are CAN bus, and brown is 5 volts. I don't know if 5 volts is going from the board down here up to the battery pack, or how that works out. But my theory is that it's coming from off of the main board through one of these pins right here and over to there, and then you go up and up the battery pack. That's my theory. And then of course both of them communicate over CAN bus. All right, so that's pretty much here as far as other components. So this is obviously a DC to DC converter right here, and here's your inductor, large capacitor, a few other small components on here, and that is an RT6362 on there, and it can handle up to 60 volts in and 2.5 amps. So in a second I'll show the underside of that board, but it is a high probability that this is making 12 volts. And coming right off of here is a MOSFET that goes right over to this connector, and that's the light connector. So yeah, this is probably 12 volts right here. Pretty high chance of that. But anyway, those small components right next to it, like probably a couple of those little resistors. Haven't actually looked at a schematic for it, but probably like those two resistors right there are like programming its output to make 12 volts. But yeah, a lot of these buck chips can make a variety of voltages. So here's the bottom side of the board. Yeah, that's going to cooperate, it looks like. All right, so this header right here is like all of your small signals going from throttle, up to the LCD, things like that. This one over here is bringing battery voltage here, and possibly bringing like the 12 volts from that DC to DC somewhere, possibly. And then you've got one small trace that goes back over to here. Anyway, yeah, mostly this is like off that DC to DC, things like that. So you can see that one leg right there that goes right over to there. That's the gate leg in this MOSFET. So that's the control signal to turn this MOSFET on and off. And by the way, this is, there you go, you can see it. So NCE01P13K, that is a 100 volt P channel MOSFET. And whenever I see P-channel MOSFETs, they get a lot of use in switching positive side off and on, or high side switching, as it's commonly used for. You don't tend to see them ever in motor controllers. Instead, those are almost all N-channel MOSFETs. So the very common places that you see P-channel MOSFETs is where you're switching battery plus, or plus 5 volts, plus 12 volts on and off. In this case here, This one being a 100 volt MOSFET, that one is switching on and off battery voltage to that DC to DC converter, which is on the other side of the board right here. This one right here, this is also a MOSFET, and that one's a smaller P-channel MOSFET, so that bigger one, that one is good for 100 volts and 13 amps, and its internal resistance is pretty high, 170 milliohms. The smaller one next to it, that one is a 55P05. That's made by a company called NCE Power. And it is 55 volts and 5 amps with 80 milliohms of internal resistance. So this one right here, you'll notice that it goes right over to this headlight connector. So that's invariably, I mean, there's a literally 100% chance of this, that this MOSFET right here is somehow or another used to turn on and off the headlight. Yeah, that's the only thing that can possibly do. I don't know what else it would possibly serve a function as. So I have a theory that there must be a button up on the handlebars dashboard that you hit a button and it turns your headlight on and off. Right? What else? How else would that work? Why would you use a MOSFET to turn on and off a headlight otherwise? All right, that's enough of the daughter board. Let's move on to the power stage. Yeah, good. It focused right off the bat. Sometimes it gives me trouble moving from one thing to another with this macro lens. Okay, so the first thing I want to talk about is here's battery minus and battery plus. And you can kind of see it here. Let me straighten these wires up a little skosh. There we go. So you'll notice battery minus, it has no vias around it at all. None. You know, you've got a fairly small solder pad here, but yeah, there's no vias around on that solder pad at all. So whatever solder gets around the wire itself is pretty much the entire current path. And by the way, over here you can see all these vias. This is battery minus 2. And inside the board, from here over to here, there's a copper plane inside this multi-layered board that's transferring battery minus over to here. So lots and lots of vias here and none here. That's stupid. Yeah, basically you've got this current choke point here and then you're going to reinforce it really good here. That makes no sense at all. None. Yeah, that's really weird. They have a ceramic cap right across battery plus to battery minus right here. And here is battery plus, and I can turn this a little bit. And I think the camera will cooperate with me. Let's see if I can't get it to focus right inside that little spot right there. Nope, it's not really cooperating so well, but you can kind of see them up inside there. There is vias for battery plus, and there is a plane that runs across the back side of the board here, and also on the underside of the board, that's battery plus. So that's fairly well reinforced, but battery minus, not so much. Yeah, all right, so the next thing here is the DC to DC, and I can get the camera to focus on that. There we go. So this chip, I had to spend a little bit of time finding it. I think that says 08B or C8A or something. Yeah, I think it's C8A. That's what it says on there, and I had to cross check that part. And that is a National Semiconductor LM5007. You know, it's an 80 volt step down switching regulator, aka a buck chip. You know, that's pretty obvious, right? You know, you've got an inductor right next to it, a bunch of small filter capacitors, you know, more ceramics for filtering. But yeah, this is invariably making 12 volts out, because that's pretty typical. Right behind it, you can see one of the MOSFETs, so G055N08, and that's that Chinese brand Huayi, Huayi. These MOSFETs are not particularly great. So yeah, that's a G055N08. They're 80 volt, 120 amp, with 5.3 milliohms of internal resistance. So in 100 volt MOSFETs, for much more amperage, you can find much better, much lower internal resistance MOSFET than this. So yeah, that was kind of disappointing to see that. One thing I do like about this though is you'll notice the TO220 package, which is this. The wide portion of the MOSFET leg is rated for 75 amps, and the skinny portion is rated for 50 amps. And these MOSFETs are butted up against the circuit board. So you can't get a more direct current path from the MOSFET to the board than this. I like seeing things like this. This is very efficient. This means that you build up very little heat in the MOSFET legs, you have the shortest possible current path, and you're using the fat part of the MOSFET on to get current in and out of the MOSFET. You're using the fat part of the MOSFET leg to get current in and out of the MOSFET. So that's very good. And they did this. I don't know why they necessarily did, but hey, that's pretty cool that they did. Kind of wish that it was that way in, say, like the ASI controllers, which are using the skinny portion of the MOSFET leg, and that sucks. That makes more heat in the MOSFET. There was something else I ran across that did that as well. But well, like say like the Necular controllers, they use the base of the fat section of the MOSFET leg. That's just fine too. But yeah, this is absolutely ideal for getting current in and out of the MOSFETs. Definitely like that one aspect. Otherwise, these controllers are kind of wah, wah. They're not really good. Right here, this circle, and you can see these two through holes, which I haven't cleared out. That is that large electrolytic capacitor that used to sit right on top of this gate driver right there. That one gate driver runs these four MOSFETs. So those are two high side, and those are the two low side MOSFETs. And obviously, here's your phase wear. Anyway, those gate drivers, they are a Chinese part. They're from a company called Fortior Tech, Fortior, and they are FD2103s. The only data sheet I could find for them is all in Chinese, so I can't tell you a whole lot about them other than that they are 180 volt MOSFETs, or I'm sorry, gate drivers for MOSFETs, and they can deliver about 1 amp. I haven't looked too much into the data sheet for these 055 N08s, but I'm guessing that they probably have a pretty high amount of gate current to need a 1 amp gate driver chip, especially for 4 of them. That's a lot. Most MOSFETs just don't need that much current. Alright, you can see right here and right here you've got two other electrolytic capacitors. They're doing more DC, battery bus filtering for low frequency ripple. I like how this comes out. This and over here is the other one. So these two through hole sets right here, everything desoldered nice and clean. That's how I like seeing it done. When I didn't succeed with that on the EBMX X9000, instead I pulled up those pin headers. That annoys me. This is what I usually get. I definitely prefer getting results like this. Okay, this little part right here, I guess before I move on, so you can see your 3 gate drivers here, here, and here. Alright, so this little chip right there, that is a quad op amp. And I think I know what it does, but hey, I could be wrong. Alright, so that little package right there is an SGM8634. It is a rail-to-rail I/O op amp. So basically, it's acting like an amplifier, and all it does is flip states. It runs on 5 volts. So whatever you feed it on the input, it's going to make basically 0 volts in or 5 volts out. Or I'm sorry, if you feed it 1s and 0s in, it's going to make 0 volts out or 5 volts out. That's pretty much all it's going to do. That's why it's called a rail-to-rail I/O amplifier. Anyway, my theory is that this CPU over here can't deliver enough current in its 1s and 0s to be able to drive the inputs at these gate drivers. And so this little guy right here is probably bumping the current up a little bit so that these guys are getting good solid 1s and 0s to turn them on and off. That's my theory. Otherwise, you don't really need a rail-to-rail I/O amplifier for anything else. Yeah, there's nothing else here that would use it. So here's your CPU, and that is another one of the STM32 kind of clone chips. This is specifically an FS32K142. It's not a particularly powerful chip. It does have an ARM Cortex M4F in it, but it works at 80 megahertz. It doesn't have very much RAM, very much CPU, so it's not really powerful. It does have a built-in UART, which basically gives you a terminal session into the CPU. It also has the CAN protocol built into it, so the CAN controller is inside the chip. Otherwise, it's probably powerful enough to do sinusoidal control. Maybe if you did a really scaled-down version of field-oriented control, maybe you could cram that in that chip, but yeah, that's probably about all it's good for. You can see a little copper nubbin sticking up here. It doesn't go through all the way, but there's another one right there. And then you really can't see them, but up underneath the back edge here, there's more of those for Battery Plus. But yeah, you can see a couple of these little things. So that's like for Battery Plus right there. and you've got copper reinforcing on the side of the board. So I did mention that this has a UART in it, and those 4 pins right there, that is the programming port. So with an FTDI to USB converter, you could plug into that thing and hack the chip, or whatever you might get out of it. I honestly don't know. Anyway, let's flip this thing over and check out the other side. There we go. Oh, come on, camera. Focus. There we go. This is on the underside of the DC to DC converter. So my theory is that these 3 little MOSFETs right there, they turn on and off something. Do they turn off the DC to DC converter, possibly? Or do they take, like, say, the 12 volts out and they disconnect that to something else? Your guess is as good as mine. I don't know. But their placement being right there like that is suspicious. And I'll talk about that in that hacking video I do. So here is battery minus. In fact, yeah, you can see the B minus on there. And then right here is battery plus. And you can see some of those vias there. And battery minus, there is no vias. Yeah, so as far as current out of the battery minus wire coming in to any place else, well, this is pretty crappy. I know for a fact that there is copper inside the board, a plane inside the board that gets over to here, but yeah, no vias here, and then you've got a ton of them over here. This is weird. That's not good. Yeah, there should be all this number of vias right here too, and there's nothing. So as far as getting current from the battery minus wired over here, well, it's really starving over here, and then it's really good over here, which is stupid. No idea why they did that. That makes no sense. Yeah, battery plus, it comes all up to here, and there's copper underneath here. In fact, you can see kind of like that square section where the copper is, and you can see like a little square section there. You can clearly see the copper underneath there. Same thing for battery minus, which is this other arc. And of course, you know, here's a phase bus, a phase bus, and a phase bus, and they all have copper in them too. So good job, Bafang, for reinforcing places that need copper. I can think of other brands that cost 10 times more money who didn't bother with things like that. So yeah, this is very good that this is in here, but you know, then no vias to get current from here to here through that internal trace. That doesn't make any sense. As far as your low side MOSFETs, that would be this one and this one right here. They are using a internal plane that comes from here, which is the battery minus bus, from there to those MOSFET legs. So there is copper inside the board that does that. In fact, like right there, you can see some of those vias just peeping out from underneath the solder work. And there's another place where you can see that too. Anyway, so that's how battery minus gets to these 2 MOSFET legs right here. Whereas like these ones here, you can see that trace going right from battery plus to that center leg and battery plus to there. So yeah, battery plus is obvious and battery minus is done inside. Right here you have 2 shunts, so that's for current sensing, for battery current sensing. Seriously doubt this controller has the brain pan to be able to calculate phase current from those. These 2 chips right here, there you go, so those are TMS 1117s, and you notice they both say, come on camera, both say 5.0 on them. Yeah, these are 5 volt linear regulators, not 3.3s. So yeah, there's no 3.3 volt linear regulation on here or DC to DC of any kind. Right here, this little chip, that is a CAN bus chip, and specifically that is the TI ISO 1042, and it's just the you know, it's just a transceiver chip. All it's doing is isolating point A to point B. And these 2 through holes right there and there, they are the orange and green wire that come from the battery pack, and they go right into the input side of this chip. So yeah, that's what its job is to basically take CAN bus signals from the CPU and send it up to the battery pack, and that's all that does. So anyway, that's pretty much everything on this board that I want to show you. Yeah, hope that helps some folks out. Just assuages your curiosity what's in a Bafang BBS HD controller. My next video, I'm going to talk about some of the ways I think you can possibly bypass the locking on this controller. Hope that helps some folks out. Enjoy. Again, subscribe, leave comments, tell your friends about my channel, etc., etc.